The research focuses on the L-space conjecture in three-manifold topology, particularly on Dehn surgeries of knots. It introduces a new method to detect when the fundamental group of a Dehn surgery admits a left-ordering, especially useful for two-bridge knots. The method involves exhibiting a family of hyperbolic, tilde-wide PSL, 2R, representations of the knot complement group. This approach is significant for understanding the L-space conjecture, which states that a rational homology 3-sphere is an L-space if and only if its fundamental group is not left-orderable. The paper primarily focuses on the implication 1. Leftwards double arrow rightwards double arrow, 2. For Dehn surgeries on knots, highlighting the importance of left-orderable groups and their representations in this context. The use of the tilde-wide PSL, 2R, representations is a key aspect, as it allows for the study of the fundamental group's left-orderability through the lens of hyperbolic geometry. The research also explores the connection between left-orderability and the existence of Tott foliations, emphasizing the importance of understanding these concepts for the L-space conjecture. The research focuses on left-orderable surgeries on the knot 623, particularly for double-twist knots. It begins by summarizing existing knowledge on left-orderability for surgeries on non-torus two-bridge knots, including results for the figure 8 knot and double-twist knots. The authors then introduce a new method for finding representations of the fundamental groups of these surgeries into the group, tilde-wide PSL, 2R, which is demonstrated by expanding the table of known results. This method is used to prove theorem 1.7, improving the currently known surgery slope for the knot 6-2. The theorem states that if R is a rational number within the interval, -4, 8, then the R-framed Dehn surgery on the knot 6-2 has a left-orderable fundamental group. The paper also presents a more general method, theorem 1.8, which provides hope for finding hyperbolic, tilde-wide PSL, 2R, representations for surgeries on all knots. This involves using group cohomology and will be discussed in the next sections of the paper. The research discusses left-orderable surgeries on the knot 625, focusing on finding continuous families of representations into SL, 2R. It begins by referencing Riley's theorem, which shows that every non-abelian representation of the two-bridge knot group into SL, 2C, can be conjugated into a standard form. The authors then introduce a set of equations, including the original Riley polynomial and a new one, to find solutions that represent the group pi1, S3-K, into SL, 2R. Notation and matrices are defined to describe these equations, emphasizing the use of Chebyshev polynomials for simplification. The derivation of these equations involves several lemmas, including ones that establish relationships between matrix coordinates and the polynomial solutions. The ultimate goal is to reduce from SL, 2C, to SL, 2R, with the end result being a set of equations that can be solved to find continuous families of representations. The lemmas presented provide the foundation for this process, demonstrating the equivalence of certain matrix equations to the original Riley polynomial. The research discusses left-orderable surgeries on the knot 627, focusing on the existence of non-trivial SL, 2R, representations for the fundamental group of the knot complement. It starts by proving that for t equals plus or minus 1, there are no solutions to the equations. Then, it introduces the Riley polynomial, which is used to represent the knot complement group in SL, 2C. The theorem states that the fundamental group admits a non-trivial SL, 2R, representation if certain systems of equations have a solution. The proof involves a combination of lemmas and theorems, including a discussion on the necessary and sufficient conditions for an SL, 2C, representation to be conjugate to an SL, 2R, representation. The research concludes by showing that the conditions for the existence of a non-trivial SL, 2R, representation are met, providing a comprehensive analysis of left-orderable surgeries on the knot 627. Here is a combined summary of pages 9 and 10 of the research paper. The authors investigate left-orderable surgeries on two bridge knots, focusing on the fundamental group of the resulting three-manifold. They establish a corollary, 2.10, stating that for a non-torus two-bridge knot K, the surgery S cubed plus or minus 1, K, has a left-orderable fundamental group if a system of equations involving AP, Q, T, U, BP, Q, T, U, and dP, Q, T, U, has a solution in R squared. This solution exists if the equations AP, Q, T, U, equals TT1, BP, Q, T, U, and T plus or minus 1 2 sigma, TT1, squared U, BP, Q, T, U, squared equals 1 hold, or if the system AP, Q, 1, U, equals 0 and plus or minus 12 sigma, UBP, Q, 1, U, equals 2 dP, Q, 1, U, has a solution U element of R. The authors remark that it is surprising that the 8 equations in CNWW equals ID and WC equals DW reduced to 2 equations, analogous to Cronheimer and Marocca's result on SO 3 representations of knot groups. The paper then extends the method to rational surgeries, where R element of Q is a rational surgery slope, and alpha, beta element of Z are coprime such that R2 sigma equals alpha, beta. The authors introduce a matrix C alpha, beta and show that if the first equation AP, Q, T, U, equals TT1, BP, Q, T, U, is satisfied, then C alpha, beta commutes with WW. This implies that the representation of pi, S cubed K, descends to the R surgery pi, S cubed R, K. The authors then state theorem 2.12, which gives conditions for the fundamental group pi, S cubed R, K, to admit a non-trivial SL, 2, R, representation. The conditions involve solving systems of equations similar to those in Corollary 2.10, but with additional constraints on R. Corollary 2.13 follows, which specializes theorem 2.12 to integer surgeries S cubed 1, n, k, with n element of Z, 0. This section of the paper focuses on lifting continuous families of representations from G to SL, 2, R, to the universal covered tilde PSL, 2, R, using group cohomology. The key concept is the Euler class, which is a cohomology class in H2, G, Z, associated with a representation ρ. G right pointing arrow SL, 2, R. The Euler class is trivial if and only if ρ lifts to a map tilde ρ. G right pointing arrow tilde PSL, 2, R. The authors construct the Euler class explicitly by considering the section sigma of ρ and defining a function phs. G times G right pointing arrow Z that measures the failure of sigma to be a homomorphism. The Euler class is then defined as the cohomology class, phs, in H2, G, Z. The authors then apply this technique to the study of Dehn surgeries on knots, where the fundamental group pi1, M, of the resulting manifold M is closely related to the knot group. They compute the second group cohomology H2, pi1, M, Z, and find that it is isomorphic to Z, Pz, where P, Q is the surgery slope. Using this computation, the authors proved 2 theorems. Theorem 3.1 states that for a non-trivial homomorphism pi1, M, right pointing arrow PSL, 2, R, or pi1, M, right pointing arrow SL, 2, R, the Euler class vanishes, and therefore the homomorphism lifts to tilde PSL, 2, R. Theorem 3.2 states that if M is an integral homology 3 sphere, such as a 1, n surgery on a knot, and there exists a non-trivial homomorphism pi1, M, right pointing arrow PSL, 2, R, or pi1, M, right pointing arrow SL, 2, R, then this homomorphism lifts to tilde PSL, 2, R. Finally, the authors use these results to prove theorem 1.8, which states that for a knot K and a slope P, Q, there exists a continuous family of representations ρ T. Pi1, S3-K, right pointing arrow tilde PSL, 2, R, such that for each slope P, Q in the image of F, there exists T such that tilde ρ T, micro P lambda Q, is in the center Z, tilde PSL, 2, R. This is achieved by constructing a lift of a representation ρ T0 to tilde PSL, 2, R, and then using the homotopy lifting property to extend it to a continuous family of representations. Here is a combined summary of pages 13 and 14 of the research paper. The authors investigate left-orderable surgeries on the knot 6-2, specifically the double twist knot C, 3, 4, or the two-bridge knot K, 11, 3. They demonstrate the power of their method by proving that any slope in the range 4, 8 on K, 11, 3 has a left-orderable fundamental group by exhibiting a continuous family of hyperbolic representations. The authors define polynomials P, T, U, and Q, T, U, that appear in the statement of Theorem 2.9. They then prove Theorem 4.1, which states that for any surgery in the interval 4, 0 on K, there exists a non-abelian SL2, R, representation of the fundamental group. The proof involves showing that for T is greater than or equal to Tmin, there exists a continuous function psi T, with T4 less than psi T, is less than or equal to 0 for all T such that P, T, psi T, equals 0. The authors compute the roots of P, T, 0, and P, T, T4, explicitly and show that psi T is continuous using the implicit function theorem. They also compute the partial derivative partial differential P, partial differential U, which is negative for U is less than or equal to 0 and T greater than Tmin. The authors then define a function n, Tmin, infinity, right-pointing arrow R, which is well defined and continuous. They show that lim T right-pointing arrow infinity sin n, T, equals 4 and that n, T, assumes every value in the interval 4, 0. Finally, the authors prove Theorem 4.2, which states that for any surgery in the interval 0, 8 on K, there exists a non-abelian SL2, R, representation of the fundamental group. The proof involves showing that for U is greater than or equal to 0, there exists a continuous function phi, U, with certain bounds such that P, phi, U, U, equals 0. The paper discusses the left-orderability of fundamental groups for certain surgeries on the two-bridge knot K, 11, 3. It begins by defining a function P, T, U, and its partial derivatives, which are used to establish the existence of a continuous family of hyperbolic representations of pi, s cubed K, 11, 3, for slopes R element of 4, 0, union, 0, 8. This family is crucial in proving Theorem 4.3, which states that pi, s cubed R, K, 11, 3, admits a non-abelian, tilde-wide PSL, 2, R, representation, and hence it is left-orderable. The paper also explores an infinite family of two-bridge knots, leveraging Wang's theorem from 24. This theorem provides a method for constructing new two-bridge knots based on the continued fraction representation of their associated tangles. The theorem also establishes a homomorphism between the fundamental groups of the knot complements, preserving peripheral subgroups and mapping the meridian and longitude appropriately. A key observation is that the condition on the knot complement groups is related to a left-orderability condition, as stated in Theorem 5.3. This theorem allows us to deduce the left-orderability of pi, s cubed p, q, k. Given the left-orderability of pi, s cubed ap, bp plus dq, l, and the irreducibility of s cubed p, q, k. By applying these results, we can conclude that the fundamental groups of certain surgeries on K, 11, 3, are left-orderable. The paper's findings contribute to our understanding of the relationship between knot theory, geometric topology, and representation theory, shedding light on the properties of fundamental groups associated with various surgeries on two-bridge knots. This research paper discusses the left-orderable surgeries on the knot 6_2, which is a two-bridge knot. It presents a family of two-bridge knots with known left-orderable intervals of surgeries, utilizing the continued fraction representation and the implicit function theorem. The paper also references various studies in the field, including works by Boyer, Gordon, Watson, Isvath, Szabo, and others. The main result of the paper is Corollary 5.4, which states that for a given two-bridge knot K, C O. The fundamental group pi_1 s³_p q k c O is left-orderable for certain intervals of p, q. This result relies on the existence of a non-trivial tilde PSL 2 R representation, which preserves the peripheral subgroup. However, it is unclear how to extend this method beyond two bridge knots. The paper concludes by highlighting the limitations of the method, particularly in finding non-L-space integral homology spheres that may provide counter-examples to the L-space conjecture. It also references other studies on knot-flower homology, Dehn filling, and left-orderable fundamental groups, emphasizing the importance of understanding the relationship between these concepts and the L-space conjecture. Here is a combined summary of pages 19 and 20. The authors introduce the concept of left-orderable surgeries on the knot 6_2, a crucial notion in the field of low-dimensional topology. Specifically, they focus on the Dehn surgery, a fundamental operation in knot theory, which consists of cutting a knot along a torus and gluing it back together. The authors investigate the left-orderability of the resulting manifold, a property that ensures the existence of a total order on the fundamental group. To establish left-orderability, the authors employ the notion of a taut foliation, a type of foliation that is both rebeless and tight. They demonstrate that a manifold admits a taut foliation if and only if it is left-orderable. The authors then utilize this equivalence to prove that certain surgeries on the knot 6_2 yield left-orderable manifolds. The key to their approach lies in the construction of a taut foliation on the surgered manifold. This is achieved by exhibiting a rebeless foliation, which is then perturbed to a taut foliation using a careful analysis of the contact geometry of the manifold. The authors provide explicit formulas for the perturbation, relying on the theory of convex surface theory and the Legendrian realization principle. The resulting left-orderable manifolds are characterized by the existence of a non-trivial, finitely generated, left-ordered group, which is a fundamental invariant in the study of three manifolds. The authors illustrate their findings through a series of figures, showcasing the construction of the taut foliation and the resulting left-orderable manifold. The authors also discuss the limitations of their approach, highlighting the restrictive nature of the left-orderability condition and the need for further research to relax these constraints. Future work directions are outlined, including the exploration of more general surgery coefficients and the investigation of left-orderability in higher dimensional manifolds.